We're continuing on section 5.1. I'm just going to do some more examples here. We are doing working example number 2, express entire radicals as mixed radicals. We're on page 190. We've already done A. Now I'm going to do B. So I'm going to rewrite B in this way. I'm going to say we're doing the cube root of y to the 7th. So 1, 2, 3, 4, 5, 6. That's like doing 7 y's. Okay, we're asking for the cube root. So we're looking at, look, this is a perfect cube, y times y, or y cubed. And this is also a perfect cube. So since they're perfect cubes, the cube root of y cubed is just y. So we're going to put we're going to take one group of 3, cube root it, and get y. We're going to take another group of 3, put another y out here. We're left with y underneath. Well, y times y is just y squared. Sorry, I should have kept my index there. Y squared times the cube root of y. That's how we would now put this entire radical into a mixed radical. Moving on to the next example. We're going to compare and order these radicals. So this says without using technology, so we're not allowed to just get out decimals and figure out these things. We're going to put them in ascending order. And if you don't know what ascending is, this helps. Ascending is from the least to the greatest. From greatest to least is called descending. So we are ascending. We're going up the escalator. Now the first thing I notice here is that all of these square roots, these are all square roots. To the 1/2 is square root. So they all have the same indices. The only one that doesn't is 13. So what I'm going to do is I'm going to write each of these as square roots. I'm going to write them in that way, and then I am going to compare them. So the first one is done. We have the square root of 149. 13 is the same as the square root of what? And I'm going to look at my table here. Well, 13 squared is 169. So I'm going to write it in that way. I'm going to say this is the square root of 169. So I've done these two. 4 root 10, I'm going to put that 4 back underneath the square root. So 4 squared is 16. 16 times 10 is 160. I've done that one. This one, 2 times the square root of 42. Well, I'm going to put this 2 back underneath. 2 squared is 4, and I have to do 4 times 42. So I'm looking at 4 times 42. I thought I got my calculator out. I guess I didn't. Where's my calculator here? Calculator, 4 times 42. There it is. 4 times 42 is 168. So I can rewrite this whole thing as the square root of 168. Okay, and then I have 3 times the square root of 19. So I'm putting 3 back in. 3 squared is 9. 9 times 19 is what I don't know. 9 times 19, and I know they said no calculator, but we could do this the old way. We could carry, but that's 171. So this is the square root of 171. Okay, it's easy to see from here what is the smallest number. Well, the square root of 149 is going to be the smallest number. Okay, next is going to come the square root of 160. Then we have the square root of 168, the square root of 169, and finally the square root of 171. And if this wasn't intuitive, just think about it. The square root of 25 compared to the square root of 16. Well, the square root of 25 is 5, the square root of 16 is 4. So the bigger number you have under here, as long as we're talking about the same indices, right? These are all squared. The bigger number you have under here, the bigger number it is. Okay? Next up, we are going to do working example number 4. We're going to add and subtract radicals. So we can only combine like terms if we have like radicals. If they have the same thing under the square root sign or under the same radicand, that's how to say that. So what we're going to do is we're going to simplify and we're going to see if we're actually can combine them. So the square root of 27 is just like the square root. We're looking for what perfect square goes into 27. Well, that's just 9 times 3. Okay, and 12, the perfect square there is 4. 4 times 3. Simplifying, the square root of 9 is 3, so we're left with 3 root 3 plus the square root of 4 is 2. So bringing that 2 out, we have 2 times 2, which is 4. Okay, we can add this up. If I have 3 square roots of 3 and another 4 square roots of 3, that's just like 7 square roots of 3. Okay, let's look at the next one. Same strategy. We are just trying to get the same radicand. We're trying to get like radicals. Well, 5 root 8 is the same as 5 times the square root of 4 times 2. I chose the number 4. I chose 8 as 4 times 2 because I know 4 is a perfect square. I'm always looking for perfect squares when I'm simplifying. So I have 5 root 8, which is 5 square root of 4 times 2 minus 3, the square root of 18. Well, the biggest square that goes into 18 is 9, so I'm going to write that as 9 times 2 plus the square root of 3. I don't think I can simplify that. Okay, here I have 5. The square root of 4 is 2, so I really have 5 times 2, root 2. Well, I'm going to simplify that right now. 5 times 2 is just 10. Okay, I have minus 3 times the square root of 9 times 2. Well, the square root of 9 is 3. 3 times 3 is 9. So I have 9 root 2 plus the square root of 3. Okay, what can I combine here? I can combine these two because they are like radicals. They both have the same index and the same radicand. This one I cannot combine. Okay, I can't add x's and y's. I can't add root 2's and root 3's. So all I can do is say I have 10 root 2's minus 9 root 2's, so I'm only left with 1 root 2, and then I still have this root 3. So that's as simple as I can make that one. Okay, let's try this last one. Oh, and we have some a's here. It says a must be greater than 0. Why did they choose that restriction? Well, let's look. We have the square root of something. If a was not greater than 0, if a was negative 3, we would have the square root of a negative number, which is imaginary, and we don't even know what that means yet. Okay? So we have 3, the square root of 32a. Well, 32, what perfect square goes the best into 32? Well, I have 4. Does that go into 32? 9? Oh, wait a second. 16 looks pretty big. So let's put 16 there. 32 is 16 times 2. So we're going to write this as 16 times 2 times a. We still have to keep that a there. Minus 4 times the square root of 162a. Well, I have no clue what goes into 162. So I'm going to get out my calculator. Where are you, calculator? Okay, and I'm going to take 162 and I'm going to start dividing it by some perfect squares. Well, let's try 16. Does that go into 16? No. 162. I'm going to look at my chart. I don't even know where to start here. 162. I wonder if, like, 64. I wonder if, yeah, I would try 64 or 81. Let's try those out. 162, oops, 162 divided by 64. Let's try 64 divided by 64. No. 162. I think 81 is going to do it. I think it's going to be 2, isn't it? Yeah, 81 is going to be our ticket. 81. So we have 81 times 2 gives us 162 times a. I should have seen that one a mile away, shouldn't have I? Okay. Well, the square root of 16 is 4. 4 times 3 is 12. We're left with root 2a minus, 4, the square root of 81 is 9. 4 times 9 is 36 times the square root of 2a. So I have 12 root 2a and I subtract 36. Well, 12 minus 36 is negative 24 times the square root of 2a. Wait a second, can we have a negative when we're talking about square roots? In this case, for sure we can. There's no square roots under the radical, which is what we're concerned about, but I can have negative 24 times the square root of 5, or sorry, rather times the square root of 25, right? That makes sense. Negative 24 times 5 is a number we can understand. Okay, so that is the end of our examples here. You have some questions to try, and make sure, if I didn't work through all these examples, the working examples, it's not a bad idea to do them because they're pretty guided, right? So if you're ever stuck, coming back and doing those might help you out.